Yes. Today we'll be talking on how to solve problems using multiple solvers. Um, this scenario comes up when you have implemented an algorithm which is quite complicated. You're not really certain what's happening inside it, uh, and this algorithm usually is based on some pattern. So you see a problem, you work something out in your notebook, and you figure out that okay, this pattern is working, but you're not sure whether it's going to work for everything. And in this case, you basically want to generate a hell lot of tests. But when you generate tests, the other thing that you need in a test, apart from your standard output, is a lot of expectations, so that you can verify that your output is matching your expectations. Uh, One of the ways you can get these expectations to work is doing it manually, but um, it's too tedious, and also if you're looking for around 1000 2000 tests, as we shall, um, it's just not feasible. So what you want is a brute force solver which has a very simple algorithm. Usually it's not efficient, but it's well known to be correct. um, if we take the example of sorting, you could have your main program implementing a merge sort, and your brute force solver probably will be implementing insertion or selection sort. Reason being, for most people, insertion sort is simpler to understand than a merge sort, and also it's rather easier to test. So the example I have picked up is of pattern matching in Java. Um, Here's the solver is implementing the KMP algorithm, and it's a little complicated. You really have to figure out that okay, where are the variables, and what kind of updates are happening in this program. While the brute force solver simply uses the index of, Java provides this inbuilt method, so why not use it? And one of the principles when writing the brute force solver is that you want this to be extremely simple to understand, and also we should never come back to it and try and figure out if anything is going wrong, because that's actually taking away your time from the main program itself. So uh, can anyone tell me the reason why we have used index of in the brute force solver, but why would we ever implement a KMP algorithm in Java if we have an index of? Well, the answer is if you actually dig deep into this, around 3000 functions later, you'll see, yeah, here. Index of uses a ON square um, pattern matching algorithm. So that's usually in comparative programming, it's not good enough. We need a ON algo here, and so we are going to be using this as a brute force solver. It's good enough for n of the order of 10,000, which takes care of most test cases. Actually, 10,000 is good enough to pretty much tell you any problem that your algo will have in the competition. So the next thing you want to look at is generating the test. So let's go through how we are going to test this. First, you could write a few random tests if you feel like, but the most important thing is generating a lot of random test cases. Here we have this random object which is going to give us you know different ints, different alphabets, whatever we want, and then we are going to take 100 cases in which we'll have a text string generated randomly. We'll take a pattern again, the exact same code, generating the pattern and the text string randomly, and then this is just converting that to a string, and finally we'll be checking assert equals checks whether this, the brute force solver's answer, is the same as the solver's answer. Remember, solver is uh, the KMP algorithm, the efficient algorithm, and brute force, as the name suggests, is a brute force not so efficient algorithm, but it's known to work. If you look at the parameters, expected is what you have from brute force. So you expect brute force to be giving you the right answers, while actual is what you have from the solver. This is the thing that you're testing, right? So let's run the test. Okay, failed. All right, let's see what's wrong here. uh, we were expecting -1 and we got an actual of 0. So what we should do in this scenario is save wherever the thing is going wrong. What are the things that we are passing into the solver? Text and pattern. We'd like to save any case where it fails. Right. In fact, you know what? So these are your two strings. Now that you have them, you can generate a new test case. Right. So before we just take the test case which was failing, we would like to reduce the size of text because it's too big, and the purpose of testing actually is not so much performance testing than figuring out the test case which is generating a wrong answer and then attacking it till the point that it starts working. So we have reduced the size of the string to 100 and increase the number of test cases so that it gets caught with higher probability. Let's see what happens. Right, I have to print the string. Yeah. So we have the two strings. The first one is the test and string text will be equal to this. The next string, which we'll call pattern, will be equal to this. And finally, we can pick up from here. That's it. So this case should fail. As you see, it fails. Now what we can do is run a debugger through solver.solve, or even walk through the code and try and figure out where in this scenario is the answer going wrong. So I already know where I have purposely messed up with the algorithm, but you can use this pattern of actually generating a lot of test cases, figuring out which one is going wrong, solving it to the point that at least this test case is taken care of, and then again falling back to generating the random test cases. And we continue doing this till we find no test cases failing. So let's just run this to be sure that the algorithm is now correct. And now let's generate the random test cases. Yeah, it works. So one final thing to do here is you'll probably be using KMP a lot in Java because of the index of not being good enough. So what we do is make a git commit message, KMP algorithm implemented, and that's it. You'll never need to worry about KMP again. Okay, I need to define a remote. I'll do that later. So that's it. Using multiple solvers is, usually very simple because your brute force solver is small and easy to understand. Your solver itself is something that you had to write anyway. So um, generating tests for it is much simpler if you use automated testing, like as shown here. Just keep generating random cases and finding the cases which fail, correcting them, and then again falling back to generating random test cases. So I hope you found this lecture useful, and I'll be seeing you in the next one, which is Java 8 features. Thank you.